To understand a torus, it helps to start with what we know, the familiar shape of a donut. But in topology, this physical, three-dimensional object contains algebraic properties that are much easier to study if we change our perspective. By unwrapping this surface, we can represent it as a flat, two-dimensional square. The arrows on these edges act as a set of instructions. They tell us exactly how to glue the sides back together to recreate that three-dimensional shape. Our goal today is to compute the fundamental group, or pi1, for two specific spaces, the torus and a more abstract shape called the dunce cap. Notice that the interior of our square here is a solid filled-in space, known as a two-cell. Translating edge gluing diagrams into algebraic equations is the core mechanic of the ciphered Van Kampen theorem. Once we can read these diagrams, we can solve complex topological problems step by step. Let's look closely at the torus square. When we follow the gluing instructions and attach the opposite edges together, an interesting thing happens to the geometry. All four corners of this square merge into a single shared point. Let's call this base point x0. Because those corners are locked to that single base point, the edges themselves transform into closed loops. The horizontal edges become one continuous loop starting and ending at x0, which we'll call alpha. The vertical edges form a second independent loop, beta. To find the group presentation, we read the perimeter of the square like a sentence. Starting from the bottom left corner and tracing clockwise, we travel forward along alpha, forward along beta, then backward against the direction of the top alpha edge, giving us alpha inverse, and finally backward down the left edge, beta inverse. This gives us our boundary word. Here is where the topology turns into algebra. Remember that the inside of this square is a solid two-dimensional cell. Any loop drawn around the boundary of a solid disk can be pulled inward and contracted to a single point. In group theory, a loop that shrinks to nothing is the identity element, so we set our boundary word equal to 1. We can take this commutator relation, alpha inverse beta inverse equals 1, and multiply both sides by beta and alpha. The equation easily rearranges to alpha beta equals beta alpha. Our fundamental group is defined by two free generators that perfectly commute with each other. A group with exactly these properties is the free abelian group of rank 2, written as Z cross Z. This diagram shows a different topological space, the n-fold dunce cap. We start with a solid disk, but this time the rule identifies points on the boundary if they are separated by a rotation of 2 pi over n. This rotational gluing rule has a specific effect. It forces every single segment along the boundary of the disk to fold into the exact same closed loop, alpha, traveling in the exact same direction. Now, think about the method we used for the torus. If you were to read the boundary word for this segmented circle, what algebraic relation would you write down? Feel free to pause and try it yourself. To trace the perimeter of this disk, we have to walk along that exact same loop, alpha, over and over again. We do this n times in a row, generating the algebraic word alpha to the nth power. Once again, because the interior of the disk is solid, that entire path around the boundary can be contracted down to a point. That means our word, alpha to the n, equals the identity element. We are left with a fundamental group that has only a single generator, and applying that generator n times brings us back to the start. That is the definition of the finite cyclic group of order n, or Z mod n. Let's look at the patterns we've uncovered. On the left, gluing the four edges of a flat square produce two independent loops that commute, giving us Z cross Z. On the right, taking a disk and gluing its perimeter into n identical segments resulted in a single loop that must be traversed n times to contract, giving us the cyclic group, Z mod n. The physical, geometric instructions for how you paste the edges of a surface together dictate the precise algebraic relations of its fundamental group. The dunce cap shows us that twisting a boundary a specific number of times means a loop can only slip off and contract to nothing if it wraps around the space repeatedly. If you found this breakdown helpful, like the video and subscribe for more visual walkthroughs of standard textbook topology.